On October 8, 2025, all eyes were on Stockholm, as the Nobel Prize in Chemistry was given to Susumu Kitagawa, Richardrobson, and omaryaghi. Their big achievement? They created metal-organic frameworks, or MOFs. These are materials that let us build with atoms like never before. This amazing discovery has led to new ideas, from catching carbon dioxide to pulling water right out of the desert air. The Nobel Committee didn't just recognize a new material, but a whole new way to design materials themselves. The story of MOFs shows how basic research can really change the world. So what exactly are MOFs? Maybe you've heard this term in the science world, but what makes them so special and often called the material of the future? Imagine a climbing frame at a playground, full of joints and bars, but this time it's super tiny, even smaller than you can see with a regular microscope. This is a simple picture of a MOF's structure at the atomic level. In MOFs, metal ions act like the joints, while organic molecules are the connecting bars. Together, they form a stiff, very neat, and, most importantly, very porous 3D network. This framework is actually mostly empty space. Imagine tiny connected holes, creating a huge internal surface area. Each pore inside a MOF can be thought of as a mini passage ready to be filled by other molecules. Just 1 gram of MOF can have a surface area equal to a football field, sometimes even more. This means there's a ton of space for other molecules to stick, store, or even react inside. What's cool is that scientists can change the size and shape of MOF pores to fit their needs. For example, they can make MOFs specifically to grab carbon dioxide from the air, or MOFs that are perfect for storing hydrogen as a future fuel. Imagine MOFs like Hermione's handbag from Harry Potter, small on the outside, but it can hold an incredible amount inside. This storage capacity is truly mind-blowing. With these unique abilities, MOFs are a game-changing material for many uses, from gas storage, air purification, to delivering medicine in the medical world. It's no wonder scientists worldwide are racing to develop MOFs for a cleaner and more efficient future. Imagine MOFs as a hotel for molecules, with each tiny hole being a perfectly sized room. Only the right-sized guests, molecules that is, can get in, which makes MOFs amazing filters. For example, MOFs can trap carbon dioxide from power plant smoke while letting other gases pass right through. Once they're full, a simple change in heat or pressure releases the trapped gas to be stored or used again. MOFs can also clean water by trapping bad stuff in their holes, leaving pure water behind. Their insides can even act like tiny factories, making chemical reactions happen with great accuracy. This level of control over molecules is what makes MOFs a game-changer in chemistry. The Nobel Prize honors 3 pioneers whose paths crossed to create MOFs. Richardrobson in Australia laid the conceptual groundwork, imagining networks built from metal centers and organic linkers. Susumu Kitagawa in Japan showed that these frameworks could absorb and release gases, proving their practical value. Omaryaghi in the United States solved the stability problem, discovering strong, crystalline MOFs with permanent porosity. Each scientist tackled different challenges, but together they built a new field from the ground up. Their collaboration across continents and decades turned a radical idea into world-changing technology. The story of MOFs is a story of vision, persistence, and global teamwork. Richardrobson's vision started with a simple question: can we build crystals like nature does, but with our own designs? This question, though it seemed simple, opened the door for amazing scientific exploration. Robson imagined a world where humans didn't just copy, but also controlled how molecules were put together, creating structures that had never existed before. He wanted to know if it was possible to design materials whose properties and shapes could be decided from the start, instead of just waiting for what nature gave us. In 1989, Robson suggested a groundbreaking idea: using metal ions as connectors and organic molecules as links to build open, three-dimensional networks by themselves. This idea was very different from old ways of doing chemistry because it focused on self-assembly and modular design. He imagined structures that could be built like construction toys, where each part had a specific job in making the whole thing. Inspired by the strong and symmetrical structure of diamonds, Robson's first experiments created the first MOF-like frameworks. He and his team tried to copy the order and strength of diamonds, but with completely new materials and methods. The result was a structure never before seen in a lab. These first materials were indeed fragile, often falling apart when the solvents were removed. But they proved that the idea of building molecular frameworks on purpose was truly possible. That fragility wasn't a failure, it was an important step in showing that a design approach, atom by atom, could be done. Robson's work became a blueprint, an early map that showed chemists they could design and build materials from the atomic level, not just rely on chance. He opened the door for the next generation of scientists to dream bigger. His ideas inspired many other researchers to look for stronger, more stable, and more useful frameworks. Every new experiment brought the scientific community closer to the revolutionary materials we now know as MOFs. Robson was a true architect who drew the first map for this molecular revolution. With his vision, he lit the fire of innovation that continues to burn today, shaping the future of material science and modern chemistry. In Japan, Susumu Kitagawa focused on making MOFs practical and stable. He found that by carefully choosing metals and linkers, he could create frameworks that breathed, expanding and contracting without falling apart. Kitagawa's MOFs could take in and let out gases like methane and carbon dioxide, showing they could be useful in the real world. He showed that changing the organic linkers could fine-tune the material's properties for specific jobs. This flexibility turned MOFs from a static idea into a dynamic and adaptable platform. Kitagawa's work proved MOFs could be stable and useful, opening the door for many applications. Omaryaghi brought precision and scale to the science of MOFs. He developed reticular chemistry, a way to connect molecular building blocks into stable, predictable frameworks. In 1999, Yaghi unveiled MOF5, a material with such a huge surface area that 1 gram could cover a soccer field. His approach allowed chemists to design MOFs on computers and build them reliably in the lab. Yaghi's method led to the creation of tens of thousands of MOFs, each one made for a specific use. His work changed MOFs from fragile curiosities into strong, useful materials. Thanks to Yaghi, MOFs are now a global platform for new ideas. The real power of MOFs is how they can help us with big problems around the world. They can grab carbon dioxide from factory smoke, which helps us clean up heavy industry. Yaghi's MOFs can even pull water right out of the desert air, giving clean water to the driest places. MOFs can clean up bad stuff from water, safely store dangerous gases, and even help break down pollution. These materials are already being used in real-world ways, from helping with climate change to cleaning our water. Kitagawa dreamed of using MOFs and green energy to turn air into useful materials, a dream that is quickly coming true. MOFs are more than just a cool science thing, they are tools for a better, more sustainable future. The 2025 Nobel Prize in Chemistry is a story of hope and human cleverness. This award isn't just about scientific discovery, it's about the power of dreams, hard work, and the belief that the future can be better. Every step in this journey shows that science is a tool to solve humanity's biggest problems, and that there's always hope for those who dare to dream and try. MOF started as a theoretical idea that seemed impossible, but through hard work and endless experiments, they grew into a real technology that is now helping to fight climate change and resource shortages. From small labs to real-world uses, the journey of MOFs proves that big new ideas often come from curiosity and sticking with it. The work of Kitagawa, Robson, and Yaghi shows that real progress comes from working together across countries and different fields of study, and from not giving up when things go wrong. They proved that science isn't just about sudden breakthroughs, but the result of teamwork, sharing ideas, and being brave enough to try new things even when they are hard. MOFs let us design materials with perfect atomic accuracy, opening doors for new energy, new medicines, and environmental solutions that we couldn't even imagine before. This technology has changed how we see resources and gives real hope for a greener, healthier future. This discovery inspires the next generation to follow their curiosity in science, knowing that every simple question can be the start of world-changing progress. Kids and teens now see that science is a way to make positive changes, and that they too can help build a better future. The story of MOFs reminds us that science brings us together in the search for a better future. Through working together, having different ideas, and helping each other, We can solve global problems and build a fairer, more lasting world for everyone. Thanks to these three award winners, we now have the tools and the hope to build a cleaner, more lasting world, one molecule at a time. Their story is an invitation for all of us to keep dreaming, keep creating new things, and keep hope alive for the generations to come.